So first I would like to thank the organizers for inviting me to present at this nice meeting. So the main question that I would like to touch upon in this talk is exactly the same question that appeared in Takanagi's talk yesterday, so I do not even bother to reword it. The strategy and approach will be quite different. So it will be based on this very famous conjecture of Hemsker, Penedonis, Polchinski, and Sully, about 8 years ago. So a question is a good one when you can see many good answers to it. And so this conjecture, so what these people did is that they look at all CFTs with classical ADS duals. They identified common features, and they gave evidence that any CFT with these properties will need to have a consistent bulk dual. So then it becomes a mathematical problem in CFTs to try to identify what exactly are the consistency conditions which ensure that you get ADS, and how do we exploit this. And of course, the first thing you do is you look at all the classic text in conformal field theories, and you see where's the formula that we need. And well, the formula is a bit hard to find, and that's why it's a conjecture. So we'll try something else, and what we'll study today are essentially we'll study something which is very Lorentzian. So we'll be looking at 4-point correlation functions, as typical in bootstrap. And so this is two Rindler wedges, and we're going to use this very convenient parameterization of the points to be in a reflection symmetric configuration, so 1 row, -1, -ρ. So we'll always stay inside these Rindler wedges. So, yeah. And most of the constraints will come from the rigid limit, and the rigid limit comes from it's a high energy scattering. It's supposed to represent high energy scattering, so you take this guy and you boost it a lot. So in terms of this coordinate, I'm going to use this coordinate, which if we were in Euclidean space, this would be complex conjugate of each other, whence the name rho and rho bar. But here these are like cone coordinates, so in the rigid limit, one of them gets large and the other gets small, with the product fixed. The key feature of the rigid limit, to get some intuition about this, it's high energy scattering, and if you draw instead of looking about flat space, if you draw the theory on the cylinder, what happens is you take an excitation at some point, and this excitation will propagate the speed of light to the bulk and reach some other point at a time shifted by pi. And then it will hit very strongly against this other particle again, this other excitation going the other way. And this limit, the physics localize very strongly in time, because we have this huge energy going both ways. And localize actually in two null directions, so we localize on transverse plane. However, there's really nothing which picks out a special transverse point. You're not focused at all. So the transverse plane, which is ADS2 ADS d-2 in this case, over which the physics is completely spread out. So this should be contrasted with other limits, where when people discuss bulk locality, you will very often talk about try to create wave packets that you can focus into the bulk and to a point. We're not going to do that today. This limit that we're going to discuss is only localizing us in time, not in the transverse coordinates. And we're going to do that because this is really the best we can do while staying within the Rindler wedges. Because if you try to focus things inside the bulk, you see you need this point and this point will have all to be time-like. So you have to exit the Rindler wedge. And it will be clear in the next few slides why we get more constraints if we stay inside these wedges. But perhaps surprisingly, just imposing locality in time, so in this picture on the left, will take us surprisingly far and imply a lot of the bulk locality constraints. I don't know how surprising it is, because in some sense we're also putting in Lorentz invariance. But I find it is surprising how far we can go, which is this picture. So let's get started. So the logic we're going to use mathematically is that locality, it's tied to, locality in time is basically causality, and it's tied mathematically to analyticity in the complex energy planes. And that, in the usual sort of S-matrix spirit, this turns into dispersion relations. So for example, if you have a gap S-matrix in flat space, this allows you to write a scattering amplitude as an integral over its imaginary part. And to derive this relation, you really need to use analyticity in the upper half plane. So this relation really encodes causality. And what's going to be the main claim of this talk is that this generalizes in any unitary CFT. So we'll be able to write the correlator in terms of some integral over its quote-unquote imaginary part. So what I would like to explain in the next, for the bulk of this talk, is what is this object? What's the imaginary part of an amplitude in conformal field theory? And why is this representation interesting? So this double discontinuity is exactly this double commutator that also appears in this study of chaos and so on. And if you think about 4 points in the Rindler space, it's basically the only way, points 1 and 4 commute with 2 and 3, so it's basically the only way the only kind of commutator you can take in this Rindler space. This has very nice properties. For example, it's positive definite. You can prove that using Cauchy-Schwarz kind of identities. You can also prove it from the OPE. It's bounded. Something which is perhaps less obvious, but also true. If you look at large n, if you take a large n C limit, you can think about the OPE between points 1 and 4. And if you look at the contribution from double trace operators, these double trace operators have exactly the dimensions such that you get integer powers, plus some small log times an anomalous dimension. But so the discontinuity is proportional to the anomalous dimension of these double trace guys. And when if you take the double commutator, you get to square this, so you get something that's very small at large n. So at large n, this double discontinuity is completely picking out just the single traces. So it's a very nice object. And an intuition for what this double discontinuity is, there are 4 terms in this commutator. You can break them out into like a time order 1, anti-time order 1, and some out of time order 1. And I want you to think that as an analogy, that time order 1 is like a scattering, it's like an S-matrix element. It tells you what's the amplitude for this guy to go across to this guy. And so it's like an amplitude. And you can always have an amplitude as like 1 plus IM. This would be the connected part. The thing which is not so obvious is what is 1 in this context. And a very good definition is think of 1 as the sort of out of time order correlator, which this is always real. So if you think of this as a matrix element and this as 1, then this double discontinuity really is the imaginary part of M. So this is a very good analogy. And to help you remember the fact that this kills all double traces at large n, you can draw a picture like that, where this imaginary part comes from cutting propagator in ADS, exactly as you would think about an imaginary part of this diagram. So once you understand what the ingredient is, it's possible to derive dispersion relations. One has to think a little bit about which variable you keep fixed. It turns out that if you keep the product fixed, you get in the complex plane of the ratio, you work in the complex plane of the ratio. It turns out that within this plane you have something which looks very much like the Mandelstam S plane. So we have a S channel, here it would be a U channel cut, a T channel cut, and if you analytically continue in the upper half plane, this is like crossing symmetry, and you have the cross channel here. So all the channels are connected continuously. And in this variable, you can, it takes a bit of work. So you think about the correlator, then you can also get a dispersion relation for this amplitude that I define, and express it in terms of this double discontinuity. There's a small glitch. It turns out, so this expression is not new. Very similar expression appeared here, and the details are in the paper. All I want to say here is that if you think about this kind of dispersion relation at fixed rho bar, it doesn't quite succeed. There's a small cut here where what the integrand is not the double discontinuity. So it almost works, And if you take the rigid limit, where this small cut shrinks to 0 and has a very small contribution which becomes vanishingly small, this really succeeds at expressing the amplitude in terms of this imaginary part. This dispersion relation has many implications. For example, once you write this, let me come back. Once you write this imaginary part, you can go into the imaginary plane and look at the imaginary part. And what you find is that this is positive. Why is that interesting? In many contexts, you have scattering which is basically elastic on the real axis. But if you go to the upper half plane, because of its energy dependence, it picks an I. And so if you know that this growing part have to have a positive coefficient, that tells you some constraint about what it multiplies. And this is essentially the key to the proof of the average null energy condition by this gentleman last year. Once you have this equation, you can take a derivative of it, and you can try to get some positive combination. Turns out that this combination is positive. And what does it mean? This tells you something about the rate of growth in the imaginary direction, which cannot be faster than linear. And once you translate this to a Wendler time variable, this is essentially the chaos bound. So this dispersion relation knows about lots of nice physics, knows about much more, and I would just like to make an analogy with something that is more familiar from the usual flat space S matrix. Is that this kind of infinitely many constraints we get there are very similar to what one gets for a gap S matrix. So we're all familiar with the fact that the imaginary part of the forward amplitude is positive. But when you have a gap, something more is true. The imaginary part is positive also in some finite range of T and for all S. It's kind of a non-physical region, but the positive T appears very naturally when you do Fourier transform to impact parameter. So in the gap theory, you have these infinitely many constraints, and the proof of these constraints is essentially the Froissart-Martin bound. And you also have bounds in this high energy behavior. And the reason this in CFT is intuitively why we get infinitely many constraints of this type, you can think of there's an effective gap because CFT is like scattering amplitude. CFT correlator is like a scattering amplitude in ADS, which is like a box. And effectively, this is why we get this gap with infinitely many constraints. So what we're going to use in this talk is this kind of dispersion relation, which encode all of the physics, but also encode much more. And we're going to try to tie that to locality. So one thing we'd like to do is to tie this to what the OP coefficients do. So for OP coefficients, in the flat space case, so again, we're going to proceed by analogy. If you start from the partial wave expansion and you plug in a dispersion relation, you can exchange the order of integration and you get a formula that expresses the partial wave coefficient in terms of integrals over imaginary parts of the physical region. And this will be positive in a range where S is between 0 and 4m squared. And this kind of formula, where the starting point only kind of makes sense for integer spin j, this formula makes sense for any spin, any complex spin, and is the basis for it's formula which tells you why amplitudes are analytic in spin. So the message here is that physically, causality or locality in time is encoded in many things. It's encoded in analyticity in the energy plane, but it's also encoded in analyticity in spin. These things are all equivalent. So in CFT, we like to just proceed the same step, do some kind of start from some kind of OPE or inverse of it, plug in the dispersion relation, and get a formula that's analytic in spin. The formula that I've shown a few slides ago is not quite good enough because of this small cut that I mentioned, and that small cut is actually important here. So, well, as to paraphrase Steve Schenker, we're going to operate a tactical retreat and change strategy. And it turns out, fortunately, that So I spent a lot of time trying to get this dispersion relation, did not succeed, but turns out you don't need it. There's a very simple way to derive this first algebra formula again. I will go quickly to this technical step, but it's basically just contour integral. So if you want to project on some Fourier coefficient, you can do an integral over this angle. It's like a contour integral in x by theta. And then you just want to close the contour. There's a subtlety that's very important, is that there's two terms here, and one term is the terms, this wj here, if you think of j as positive, this term is small in the middle, so you want to close this contour to the origin, and you want to close this contour out. In this variable, there's a symmetry between w and 1 over w, so these two things really give you the same thing, but to do the manipulation, you really have to separate the two terms. And then this integral over the cut of the amplitude, which gives you integral over its imaginary part. So in CFT, we do the same. I'm going to briefly flash through this. So we start from the Euclidean OPE, which Fernando reviewed this morning. So you express the correlator, which is a function of two cross ratios as a sum of conformal blocks with some coefficients. This is discrete in two ways. The spins are discrete, the dimensions are discrete. It's actually useful to make the dimensions continuous at the first step. Thankfully, this was done by this gentleman before. And so you can write, basically, physically, you should think of this integral as like a Millen transform. So dimension is Millen conjugate to a space-time distance, and this is just basically a Millen transform. And these two formulas, the one on top and the second, they match provided that these coefficient functions have poles at their correct place. But the ingredient, something which is a bit surprising, perhaps, is that what you need here is not the usual conformal block, but it's what is called as harmonic function. And this is a much nicer function, which has a single value in its property. So it's not quite the same function. Nevertheless, the two formulas agree. So then, the nice thing about this harmonic function is that this obey orthogonality relation. So to invert this formula, you just have to integrate against it. So it's basically for the group theory, it's just some orthogonality relation for the principal series. And in practice, for those who have not seen these words, it's really just works exactly the same way as a Millen transform. So you can invert these coefficients. So now that we have this formula, so this is pretty much analogous to this formula where you had this integral over this cosine before. Our next step is to split this block into two parts, one of which vanish at the origin and one of which vanish at infinity. So we want to split this block into two parts like that. So that is the actual calculation we have to do. It's a bit tricky because for cosine, there's like two obvious things to use. X, there's two exponentials. For this guy, there's like 8 solutions to the same Casimir equations. And they all talk to each other somehow when you go to various limits. You find two combinations which are nice in the origin and infinity. So that gives you 4 parameters and 8 constraints to express this f. So there's 2 parameters here, 8 coefficients to fix. This is the place where it talks just weird because I have no explanation, but there's a solution. So there has to be more constraints than parameters because there should only be a solution when the spin is an integer, because so far the spin is an integer. It's not obvious why there's a solution except from the fact that we expect a dispersion relation to exist. So the result is the following. So I have a formula which expresses all S-channel OP coefficient in terms of some integral over a special block, which is basically a usual block with spin and dimension exchange. Explain that. And the key ingredient is that it involves this double discontinuity, which we've seen is the analog of the imaginary part of the amplitude. So this formula, you input the imaginary part of the amplitude, and you get out the full amplitude. And you can show that it converges for spin greater than 1. You can prove this using known convergence properties of the OPE. So there's some application tests. So okay, the first thing I did is try this for 2D Ising and hope that it works. So first step, you take this result, you take its double discontinuity, it's positive, like it should. This theory makes sense. Then you have to integrate it against this block. And there, so the idea is that, okay, this is sum of two Virasoro blocks, but what we've been using so far are the global blocks. So when you expand this guy into global blocks, you get infinitely many things. So you have to integrate this guy against its blocks. The blocks are factorized, so you get a product of two integrals, which should not be 3f2s. And then you get take residue of this formula, you get the OP coefficients, and you can match these with the OP. So I don't know if this result was known before, I know how to decompose the Virasoro blocks into global blocks, but this formula does it, and it works. So now I want to discuss somewhat more interesting application. So Fernando nicely described what we can do at large spin using the bootstrap, and his story was based on looking at this double Lycone limit, where you can use the OP in both channels, and they converge nicely. And then what he explained is that if you have some non-analytic behavior in one variable, this requires an infinite sum in the other channel to reproduce it, and that tells you something about the tail of that sum. And so it's the usual thing about duality is that large quantum number in one channel is tied to a small quantum number in the other channel. So the leading twist in one channel is tied to large spin in the other. And using this, people found a way to solve the OP in a asymptotic series in 1/spin. So what you can do is you can start from this formula that I wrote, and you can just say, well, look, let's take the spin large and see what happens. So, well, the formula is stated as a two-fold integral, but really what happens, so this should be rho to be consistent. What you really remember to extract OP coefficient, you're supposed to extract poles, and these poles come from when one variable goes to 0. So it's really only one integral to do. And that integral to do, when the spin is large, you just get pushed the corner that, you have this big power here, which pushes you to z bar equal 1. So you stare at this integral, and you immediately see that indeed you're pushed to that corner. So it's consistent. And you can do the integral for some simple power law, and you can get some analytic result. And that result matches exactly what people do. So essentially, we can restate what is done by this bootstrap approach is that you expand the cross-channel OP in power of this variable, and you use this result for the integral of a power, and that reproduces exactly these expansions that Fernando discussed this morning. So as an application, for example, you get is what you get in 3D Ising. So if you include only like delta epsilon and the stress tensor, simplest guys on the right-hand side, you get this prediction for the double twist operators, and it matches. It just works all the way to stress tensor. It's beautiful. In principle, this was an approximation at large spin, but here what is new is that you really, this 1/spin expansion, you really don't have to expand in 1/spin. You can really just, you don't have to expand this variable. You can just do the integrals numerically and check that it works. You also have control over all the other guys, like this guy could not stick out. It really has to be there. You have to get individual controls, try to bound errors. So yeah, now I want to go to the main part of this main message of this talk. So let's see how this formula pertains to bulk locality. So here's a formula for how you evaluate this double discontinuity in terms of the cross-channel expansion. So you see, because it's a double discontinuity, you get this sine square of anomalous dimension. And because of this, you're basically killing all double traces, leading order 1/n. And I've drawn this little figure here just to see that if you were to keep this term, it will tell you basically that the first 1/n correction, the loop in ADS, is basically computed as a square of this anomalous dimension, which you get from tree-level data. So this nicely makes contacts between what the method that is essentially what Fernando used this morning, and can make this picture allows you to make contact with the unitarity method. This method to compute loops. And the other thing about this figure, if you look at single traces, in theories that are that have ADS CFT duals, there are very few liked single traces. And the heavy ones, you see, unless rho is very small, these heavy ones will be exponentially small. So you can see that almost everywhere. So this gives a very simple interpretation of this criterion that Polshinsky et al. propose. So the theories with classical ADS developed are simply those CFTs where this double discontinuity is saturated by a finite sum of a few guys. So this two, the criterion is equivalent to that. So if you make a plot, so this double discontinuity for most of the range is proportional to 1 over NC squared because you're looking at the connected part. But this comes from just a sum of a finite number of liked operators. And then as you reach as you go to extreme cross ratios, the heavy guys kick in, and eventually also the 1 over n correction, and all the other guys, they kick in, and you have some non-positive physics. What is very important about this plot is that we know nothing about this part of the curve. It's all U ultraviolet input. But what is very nice about this object, double discontinuity, is that we know it's bounded by 1, and we know it's only so wide. So even though we know nothing about this, there's only so much area you can squeeze there. And then you're supposed to integrate against this curve. So when you integrate against this curve, the bulk of it gives you something about, give you the liked operator contribution, which essentially will be what people call a minimal solution to the crossing equation. And the rest here will give you some little extra thing, but because there's only so much area you can squeeze there, this will be something that you can bound. And as you increase the spin, you have to integrate against rho to this power of j, so it gets smaller and smaller with increasing spin. So you have a contribution which is not smaller with increasing spin, but which you know completely, plus something which decays with spin. And you can bound it. And this bound you can interpret very nicely in terms of effective theory in ADS. So if you imagine a heavy particle in ADS, you integrate it out, you get a series expansion in the power of s to delta square. And each power of s carries like 1 unit of spin in the Regge limit. So you get exactly this delta square to the delta to the 2j. So the suppression is exactly what you expect from effective theory. So in some sense, this formula justifies the use of, from a CFT perspective, it allows you to justify using bulk effective field theory. It does not completely justify it because of this, what I mentioned, we're controlling the spin of an interaction in ADS, not its scaling dimension. That's because we're not localizing the transverse directions. But so there's a handful of interaction, like if you have a 6-derivative scalar interaction, it will not be constrained, because it behaves like spin 2 in each channel. But if you scatter gravitons, for example, things get more and more constrained, and there's actually only one unconstrained coefficient for graviton, and for 4 gravitons, there's no free parameters. So basically, you constrain every higher dimension operator, you can constrain it to be small, except for a handful of ones. Yeah. So this is the summary. So discuss dispersion, discuss a dispersion relation, which gives you OP coefficient in terms of a certain imaginary part of the amplitude. The input are essentially CFT versions of analysis positivity that were used also in by Froissart and Martin in the 60s. They're literally the same. And the output is you can do large spin expansions and try to control the errors. You can express ADS CFT correlators in terms of a few liked fields, and you can get bound on the errors on the contribution from the other ones that parallel what you expect from bulk locality. Thank you.
Questions? Over there.
Hello. Hi. So say you have an unstable particle. Here, Simone. Hey. So you have an unstable particle in ADS whose lifetime is long compared to the ADS time.
Yes.
So how do I think about the lifetime in terms of the CFT? Can you somehow say what that is in terms of operator dimensions or?
Yeah, if it decays to, yeah, it's a good question. Yeah, if it has a finite lifetime, then it decays to some lighter stuff, so it will not be a CFT operator by itself, but it will be some kind of resonance that you can see by producing other things. I don't know if people have looked at that in the bootstrap. I don't have anything deep to say about that. But yeah, you will see it at effectively as some resonance. But
yeah, there.
So I believe that for the S matrix, in general, the analytic properties are more complicated than is required for the dispersion relations you started with.
Yeah,
Because-
this is one important point. So the analytic properties in the CFTs are actually much easier to prove and use than those in field theories. The ones which are, I think, are analogous to the one we use are the ones which are rigorously proved. I mean, we expect more to be true, but this thing has been proved by Froissart and Martin, is that if you take T in that range, then you have an LST in the complex S-plane minus the expected cuts. And that I think is very much analogous to what we use in CFT. But in CFTs, it's actually much easier to prove, which is interesting. Then the analogous statement that we needed in the rho bar plane is easier to prove. That's what I mean.
So some statements you made about the S matrix are not really true in general, but you think that the analogous statements in CFT really are true. What's basically not true in field theory is that the S matrix only has S and G channel cuts. There are
Yeah.
things called anomalous thresholds and so on.
Yes, yeah. I think this region avoids, as far as I understand,
Okay.
avoids them, yeah.
More questions? Okay, then let's thank the speaker again.